All right, guys, it's 3:10. I believe Steven's still in a breakout room, but we can begin right now. So welcome to the PCB workshop held by IEEE. Today we're just going over an intro to Altium and PCB fabrication. So this workshop is being run by myself, Selena. I'm a second-year ECE, and then Fahim.
Greetings, hello everyone.
Yep. So we have a short introduction here. So for our agenda, we'll first go over what PCB fabrication is, and then we'll go over what Altium is, and then we'll talk a little bit about the circuit that we'll make today. Oh, Steven's back. Do you want to introduce yourself real quick?
Yeah, sure. Hey guys, I'm Steven. I'll be helping with running this workshop as well.
All right, cool. So like I said, we'll go over the circuit that we'll be making today, which is an audio amplifier, and then we'll jump directly into Altium. And the goal of this workshop is that you'll all be following along with me so that we can go through like all the steps together. And if you guys have any problems with Altium or any step, just like type in the chat and a mentor will bring you to a breakout room or try to answer your question in the chat. Okay, are there any questions so far? Okay, cool. So, Beam, take it away.
Greetings everyone. I hope you guys can hear me well. If not, feel free to type in the chat. We're going to start off with a quick PCB fabrication overview. Although it's going to be quite brief because the fabrication of a PCB itself doesn't need to be within our concern too much as a designer. We leave all the details with the manufacturer whom we will send our designs to at the end. We just need to be concerned with how to design the PCB itself. So the specifications as to how thick the traces need to be, how to actually connect from one pin to another, and the traces that go in between them, as well as the thickness and the number of layers that PCB entails, among many other factors. As you can see in the hyperlink in our slideshow, which hopefully you have access to, there is a PCB design document that we've created that outlines the general steps that are taken when you plan and design a PCB of your own, which we will go through all of in our workshop today. I'll hand it over to Steven.
Yeah, so the reason we're going to be using Altium is because it's industry standard electronic design automation software. So in terms of creating PCBs, it's like the gold standard. Alternatives for EDA software include Autodesk Eagle, KiCad, Easy EDA. These are all viable options as well if you want to create a PCB. Do you want a next slide?
Yeah, go ahead.
Okay, so the audio amplifier we're going to be using in this workshop is the circuit that we're going to be using in this workshop is an audio amplifier based around an LM386 IC. This is a Texas Instrument IC that just acts as an op-amp. And we're going to be making just an amplifier for a microphone signal and then attaching the output to just a 8 ohm 0.25 watt speaker. Cool. And here you see a list of components.
Right.
Great, let's get started.
Yep, okay. So now we're switching to Altium. So just open your Altium software program and we'll start following along doing the designing our PCB together. So if you, again, like, it's okay if you bump into any problems, just let us know and then we can try and help you out. And presentation slides are in the link. Okay, so when you open up, you'll be on this home page here. And the first thing you want to do is create a project. So you can do file, new, and then create a project. You can name your project, and set your folder. Create it, and you'll see your panels pop up. Just give it a moment. Okay, so this will be your project right here. We can ignore that for now. Does everyone see this panels sidebar? You can type in the chat.
If you are unable to see it, there should be a button on the bottom right-hand corner of the window saying panels, and just click on that and you can choose which panels to appear on screen.
Yep. Is everyone here or don't see any feedback in the chat yet? Cool. That's good. Hunter sees it.
Thank you, Hunter.
Okay, great. Okay, people are seeing it. So now they've created a project. First thing we want to make is a schematic. So we can do project and then add new to project and then schematic. So when you click this, you'll have this new sheet right here. And this is where you'll be just laying down your different components and your wiring. So let me know if you guys have this sheet created. When you create this sheet, you want to press Control S and save it first. So this will be, you can name it what you want. We'll just do audio app schematic and save it in your projects folder so that you see it now underneath your project file. Let me know if you guys have any problems with that. Okay, yeah, go ahead.
Sorry to cut you off there. I just wanted to make a quick note that at the very bottom right-hand corner, you can see a bunch of subtitles, one saying title and other saying number. I just want to draw your attention to the size. It says A4 at the moment. That is adjustable. We're only choosing A4 right now because our circuit schematic itself isn't going to be particularly large or particularly tedious. But for more tedious circuitry where there's more wires and everything will be a bit more clustered, unless otherwise, you're going to have to increase the size. But for now, A4 is fine for us.
Yeah, so actually we can talk about sort of the layout of the interface right now. Yeah, okay. So down here you can see a panels button. So we want to open some of the panels that are important to us. So one of them is components. Another one is manufacturing part search and properties. So for now, like those will be important for us to use. So let me know if you guys can get those panels out. Right, okay, so then up here we have the different tools that you can use. You got wiring, ports, and you can create sheets and text and arcs and all that. So that's where all your like placement is. But you can also just, right click and also go to place and you'll have all the tools there for you as well.
And quickly to build on top of that, Altium also has a large array of kind of shortcut keys to actually access a lot of these, and I think they're all configurable as well. So you can also go and do that if you have, shortcut, if you want to create shortcuts for different things.
Yeah, so like up here you can, for now, like without customization, you can see that like whatever is underlined, like you press T, that will open tools, and you press P, that will be place. So those are just some shortcuts. Okay, let me know if I'm going a little too fast or too slow, and I can adjust accordingly. So does everyone have this sheet and have your panels open? Feedback in the chat. Yep, okay, great. So first thing, we want to add components. So for our schematic, we want to create, we have a components list that you saw on the slides, and this is what we'll be following. So in the manufacturing part search, in Altium has this manufacturer part search, which is really great because it has like all the parts here for you, which has like the schematics and the footprints and all the information that you need already set up. So a lot of it is already available to you here and doesn't require you to go through a lot of the details of creating the schematic and the footprint yourself. We'll be going over that later on in this workshop, but for now we can add the components just to get an idea of how you can create the schematic using this. Also for clubs, usually you guys have your own integrated library, and that you'll usually be using that. And if you're creating any custom components for your clubs or for yourself, that will be added on, which we'll talk about in a bit. So in the components here, list of components, we can first add our op-amp, which is the most important part, that will be controlling our gain. So give me one sec. Just zoom in a little. Okay, so you can just sort of copy and paste the component into here and it will search it automatically for you. You have this here. You want to just, oh, okay, TM struggling. You want to just click and drag onto the schematic. So this will just search it up and you'll see that down here, you sort of have all the information. You have the models, which is the schematic, and you have the footprint, which is basically like a 3D model, but if you go into 2D, this is like the footprint that we'll be using in layout later on. But you don't have to worry about that just yet. Mainly just the schematic.
Another thing is if you see that like little chipset thing, that like green little chip thing next to the component there, that means it does have a footprint and it does have a schematic print. But if you don't see that, then you can't really place it. So there's a lot of manufactured parts that are out there that don't have this, and that will require you to actually go and build your component and then kind of add the parameters into it.
Yep. Okay. There's a comment in the chat. I'm a little bit behind under the project panel. Oh, okay. Project here, add new to project. Do you see this? So first you have to create your project. So make sure you have created your project and saved your project and then, okay, perfect. Awesome. Okay, so we'll first just drag all our components onto the schematic and then we can go from there. I hope you guys have the component sheet and then I'm really just copy and pasting the components just to save some time. Usually this does take a while. Oops. Oh, okay. All right, not manufactured part search. All right. Okay, so this is our potentiometer.
Hello, Selena, I'm not sure if this is on your end, but I'm having trouble hearing you as well.
Oh, can you hear me now?
Yeah.
Yes.
Oh, okay. Sorry, I muted my mic accidentally. Okay, so
Maybe go back.
Yeah.
Go back like 20 seconds.
Yeah, sure.
Perfect.
So, yeah, so for now we can just place all our components on the schematic and then we can go from there. So I was just saying we can first, I hope everyone's using the component list and just copy and paste the component serial number onto here in the search bar in the manufacturing part search. This is where you'll find all the components that you can use with the footprint and the schematic. If you have any problems with that, just let us know. You can just click and drag it onto here. So we have the potentiometer, which we'll use to adjust our IC, and then we have the microphone, which is what we'll be using for our input. So this is the mic, this is potentiometer, and then for the power source and for the output speakers, we won't have it on this board. We'll have it as a exterior component. So we'll use two connectors for those two components right now. And the connector we've decided to use is the screw terminal. So I think most of us are familiar with the screw terminal. So again, these components are your first stage of PCB design is figuring out what kind of components work for your circuit. So obviously you guys want to do that for your own circuit first and make sure you know what components you need. and then see if it's available here. Most of them will be, but if they're not, you'll have to create a custom component, which we'll show you how to do later. Okay, how's everyone doing so far? Is it
Yep,
good?
I've been informed the list in the slideshow is an image, and they can't actually copy paste the values. So I'm just going to update that real quick. Hold
Okay.
on, everyone.
Thank you for that, Stephen. I believe that it should be a good time for us to have a bit of a discussion onto the data sheet of the LM386, as to we've already placed the majority of the other parts. So Selena, if you don't mind giving me control, so
Yeah.
I can.
Let me just pull up the data sheet first.
Yeah, no worries.
Yeah. So this is the data sheet for the IC, and then remote control. There we go. Okay, Fahim, do you have control?
Yes, ma'am. All right. So there's going to be a bit of latency on my end, so I apologize for that. So yes, as you can see here, this is our data sheet for the LM386 audio amplifier, like the op-amp itself. Typically in a data sheet, since when you make any PCB design project, or really any electrical project at all, you have to search through several components to see what exactly fits the specifications of your design goals. And so typically the first page gives you a really good insight into what the component itself does and what is required from it. So in our case, all we need to do is look at the features list to see what it's capable of. So in our case, our voltage gains go from 220 to 200, which if our gains require something higher, then this would be inadequate, and we need to search for other components to fit the bill. But in our case, it's fine. We're not too concerned about the other parameters, or the other design features rather, because they also meet our specifications. And if you're wondering what a particular component does, you can always look at under the applications. Looking at the description gives you a good insight into it. Of course, I think what gives the best insight is the schematic itself. As you can see here, the schematic is a top-level view of the inner workings of the component itself. In our case, you can see here that there's a certain class of transistor amplifier. I believe it's called a transistor BJT amplifier, used at both the inputs, both positive and negative terminals. And with the usage of this 1.35K resistor, we get a particular voltage output at pin terminal 5. The rest of the circuitry is used for like diode switching and current management, which is why you see the diodes here and the resistors here. Now, all that is great and all. However, if you want to look into these specifications a bit further, you're going to have to look at the particular values. So before I go on to that, here's another picture of the pins themselves. As you saw earlier, Selena was able to find a footprint where all the pins were already readily available. However, that won't always be the case. If in the event that you do need to make your own footprint, the pin configuration and functions, which for Texas Instrument is under the header number 5, it'll give you a good insight on how to design your footprint. Here's the description of the pins, and as you scroll down, you see more and more numbers that are used as metrics for the design for the component in question. Of course, you can read through all of them, but if your only concern is to be wary of a particular set number of values, then you only really need to look at those particular numbers. In our case, that could be total harmonic distortion, bandwidth, power supply rejection ratio, so on and so forth. Output power. For us, we're not too concerned with this one because all we're doing is driving a audio, like a speaker, and in our calculations, our wattage is around 0.5 milliwatts. So as you scroll down, you can see all these characteristics with the current and the voltage. This is more of you don't really need to worry about this too much. It's more of a research like that you're looking into for the component itself. What I want to draw your attention to next, however, is probably the most useful part of the data sheet, which is actually seeing example circuits. So as you can see, and I promise I'll get back to it. So the first one here, for Texas Instruments, again, the heading is number 9. you see that there's a typical application with a gain of 20. Underneath here, we can see a particular setup for the circuit. And what's really nice about it is that they give you an example of what it could look like. And just from looking at this at a glance, you can tell that if you leave pins 1 and 8 open, you automatically get a gain of 20. So that's good to know just at a glance, right? Say, for example, you wanted a gain of 0 to 19, for example, you know that that wouldn't be possible. You know that the gain strictly has to be a minimum of 20 for a particular op-amp. And as you scroll down, you'll be able to see that there's a circuit for a gain of 200, which we'll be doing our best to emulate in a way that considers other safety factors in mind. I'm going to wrap up my discussion very quickly so that we can get back to designing with Altium. But I just want to bring your attention to the measurements at the very bottom of the package itself. And the reason we want to look at these is going to be for a later stage of our workshop, where we're going to talk about how to design footprints. These measurements are going to be very useful in the event that we need to design the footprint for the component. And so you're going to have to consistently refer to the datasheet in particular for this, if not anything else, for the custom component footprint that you're designing. With that, I'll hand it back over to Selena.
Okay, great, thanks. Yeah, so we'll be looking at this later for the footprint. For now, let's continue. Now that the table should be on the slide, we should be able to add all our components now. Another short key I was mentioning when I was muted is that if you're holding onto a component, you can press the space bar and that automatically rotates it. So actually we want it to be facing this way. Okay. So for our second capacitor, we have this. Please let us know if you have any problems with like adding these components onto your schematic. Okay, so we have this one as C1. So when you double click, you'll be open to like all the adjustments you can do to the component. So the main thing is like the designator and the value. So the value for the first one that we just added, so it should be on the table, but the name, it's important to add the name, which is C1. And then for this, it is C2. Oops. Right. Fahim. Wait, Fahim, give me a second. I think you are still controlling. Stop control. Okay.
Also, Fahim, I think you're muted.
Oh, yeah. I actually went to click the unmute button, and that's when I took control. So my apologies.
Okay. No problem. Okay. This is just the bit that is a little mundane. And then after this, we get to start wiring. C4. We have 5 capacitors total, and then 2 resistors that we'll be adding. And Fahim will be talking about why we've chosen these and how the circuit sort of functions.
Yep. I can start my discussion at the moment, if you wouldn't mind.
Sure. Yeah.
So essentially, if you guys are wondering about the different components, so our microphone at the beginning, optionally we could have chose to go the super, how do I say, botched method, which is to, you know, take like a piece of like your headphones, for example, cut it, and then use the 2 wires in your headphones and the audio jack on the other side, and then solder those wires in, and then essentially literally have a speaker built just from like plugging in the audio jack to your phone, for example. But we just thought that the microphone itself would just be more elegant so that somebody can just like talk into it rather than having to cut off their headphones. The potentiometer is there for volume control. So optionally, we could have done it at the output as well, but we're just able to control more of this output, like I guess you can say swing, or like the range at which the output increases its volume by having it attached at the input instead of at the output. The connectors themselves, although sort of deceiving based on how it looks like, the wires 1 and 2 point towards the circuit, as that's where, as it'll be connected to the circuit. The screw terminals on the other side are actually, you can actually lift them up by using a screwdriver. And what happens is you can connect the ends of another wire into the screws, screw them down, and you have a wired connection between the wires that are open and the screws. Of course, there are some safety concerns with that, but we're not driving too much current, so there isn't too much of an issue there.
Okay, yeah, I think we are about done adding the components and naming their values here. Is everyone sort of following? Let's see, just some feedback in chat would be great. Yeah, so Jay is asking manufacturing part search. You can click your panels button down at the bottom right, and then you'll have a list of different panels you can open up. And this is the manufacturing part search. So if you click on it, it should open. I'll give people some time to add it because it can be a little slow. C_J.
I can take this one. So essentially, if you're talking about the like what's on top of each of the elements, they're called designators. And although the standards have changed throughout time, typically the designators for components help the program, in our case Altium, define each of the like components and what they're used for. So for example, whenever we designate the use the designator C question mark, it means that there's a capacitor there, and like there's an associated value of a capacitance that's with it. For resistors, it's R question mark, which we later rename as R1, R2, R3, and so on and so forth. And with connectors, it's J. And as you can see at the very beginning, for the microphone, it's LS.
Yep, and ICs are usually U, MOSFETs Q. These are just conventions that sort of go along. Yeah. Any other questions?
Feel free to ask away.
Yeah. Also, let us know if we're going too fast or if we can move on to the next step. So if you're done, just let us know. If you're not, just tell us to wait a little bit and we will. Okay. Oops. Okay, cool. So I think most people are finishing up. So we can talk about placement now. So from our schematic, we want to have, okay, so we know that the input is the microphone here, but we can first talk about the output of the IC. So V out, we know it's going to go to the J2 connector, and this will go towards our speaker. So just as like our schematic, like you would plan this out beforehand, but we know we'd want to, actually we can see this in the data sheet. Let's just take a look real quick. If we can remember, yeah, okay. So you can, this is from the layout, but you can see there's a capacitor and also a capacitor resistor goes to ground. So we can just take that from, we'll have this like planned out beforehand if it was your own circuit. So to place a wire, you can take these two like parallel line sort of thing, and you can just click on the edge of a wire and click it to the next connection. So for us, this will go towards R1, and this then will go to C2, and C2 will go to ground. To place a ground port, you can click this bar right here, and it will get you a ground, and you can rotate it, place it where you want. So, but if you want a power port, you can right click on this and you'll get all these options to place like a VCC, 12 volt, 5 volt. And if you, you can place like just a power bar and it says ground, but you can double click it and change it to like 12 volts. And that will just let Altium know that that's a 12 volt bar right there. Okay, wait. There we go. Okay, so let's connect this to ground. And then we've got C5 that goes from from here. And this goes to the first pin of J2. So let's actually move this up. You want to make your, like, the point of the schematic is to be as clear as possible so that if another engineer was looking at your schematic, they'd be able to like understand what's going on. So you don't want to have wires like going in just nonsensical directions. You want to keep it clean. So I think while we're doing this, because it's again sort of just like, trace the wires and you can sort of follow on, along on the screen, Fahim can describe to you like what is happening for each part. So yeah.
Thank you, Selena. So we can start off with the, I guess you can say the pin 5 node, where it's connected to R1 and C5 and by extension to R1, C2. Essentially, we have that because we don't want to have, so the reason we have R1, I guess you can say attached in parallel to the C5 capacitor and the output that follows it, is that we want to limit the current that the output sees, because the speaker that we're trying to supply power to only needs a couple of milliamps of current. It doesn't have that much resistance in it. So if we supply too much voltage, we'll drive too much current to the output and we'll end up breaking it or heating it up too much, and then which causes overheating. We also have capacitor C2 there. In the event that we need to draw more current from our output into the, from the ground that it's being drained to the output. You might be wondering why we have the capacitor C5 there. The C5 capacitor is typically a relatively large capacitance for the express reason we want to filter out DC voltage, because we do not want DC voltages at our output, since we're just trying to amplify the AC voltages from our speaker, or from our microphone. DC voltages are pretty harmful for the speaker because, as I've said, it's a very low resistance. So if we put too much current through it, we'll be able to fry it. So we want to avoid that as much as possible. And on a final note, if you may be wondering why we're using different capacitors, that's because certain capacitors every capacitor has its own type, and some types are better than others. For example, our capacitor C2, if I'm not mistaken, is a ceramic capacitor, meaning that it typically won't have particularly high capacitances, but it's very good at discharging, much better than an electrolytic one, which is better at just storing charge over time, which is a good example of that would be our capacitor C5. As you can see here, Selena has had a capacitor C3 directly at the terminals of both the gains for 1 and 8. If you happen to have the data sheet opened up, you'll notice that for the example diagram, I believe it was 9.2 if I remember correctly, has a gain of 200, given that you have a capacitor, with, I think if it was 10 microfarads connected between these two ports. You may be wondering how any current flows at all if there's just a capacitor in there. Well, that's because in our schematic that we have seen at the very first page, there's actually a 1.35K resistor in parallel, or like already connected between the terminals of 1 and 8. So connecting a capacitor is really just connecting the capacitor in parallel with the resistor that's already there. As you can see here, we have on our pin number 7, we attached a bypass. Same thing with our pin number, pin number 2 on the J1 connector. These are both bypass capacitors, which are meant to store charge that's going to be later used by our op-amp if needed. For the C4, it's more specifically to do with the power supply that we provided, which is also connected to, pin number 6, which is VS on the op-amp, which is tied to the pin 1 of our J1 connector. So this is in the event that we need to draw a large amount of, we go from drawing a low amount of voltage to a higher amount of voltage. And so if the power supply isn't ready for that very quick rise time or very quick rise in voltage, then our capacitor will suffice for it. And as you can see here, Selena connected the potentiometer appropriately to adjust for the volume between the inputs.
Yeah. Okay, so I just put a note here. that we don't need this resistor. So notes are good to put on your schematic as well, especially if it gets a little complicated, it might not be clear to someone else looking at the schematic. So you can add notes. So we're actually gonna just delete this resistor.
If you're wondering why we had that resistor on the components list to begin with, it's because the only reason we don't need a resistor, we only need the resistor to be tied with the gain if we want to reach a gain in between 20 and 200. But since we wanted to get the maximum gain, there would be no point for a resistor, as it would be draining needless amounts of power that we wouldn't need. Since we're not trying to limit the gain, there's no point for it. So for that reason, we've set to exclude it for our schematic.
All right, so something we can do, because it might not be clear, going back to the notes thing, it might not be clear to someone else watching or looking if it's like which connector is to which port. Usually if you have like different PCBs connected with each other, you can just put a power port, which will show like, oh, it's going to like the power rail. But if you have like an entire system that you're working with, but since we just have screw connectors here, you can go to place and you can press note and you can place a note here. So this connector is actually one connector. It's actually going to our battery source. And our pin 2 is to ground. Our pin 1 will go to a 9-volt source.
Selena, we have a quick question in the Zoom chat.
Yeah.
So they're just wondering how you make the wires jump over each other.
Yeah, so if you just place a wire that goes over another wire, it will automatically jump over. And then if you place a wire that actually connects to the wire, it'll create the dot so that it's obvious which one it is. Oh, okay.
It might depend on the Altium version too. Did you get the latest version, Sana?
Yeah, I'm 20.1.14.
Yeah, because before they didn't do that, or I mean, it depends on your Altium version. If you're using a newer version, it should be an issue. But
Oh, okay. Is it in preferences?
anyways, I have the same thing. As long as there's no junction point, it's not connected. Worst comes to worst, you can always put nets. Have you gone over nets yet?
No, I was just about to go into nets.
Yeah, so you can, if it's crossing over like that and it's too like cluttered, you can do nets, and Selena will just go over nets in a sec. So
yeah, there's just a couple questions. Let's just if Jay, you meant how do you rotate the comments? If you want to rotate like a component, you mean, you can just hold on to it and then press spacebar and it'll rotate. Okay. Permanent journals. Okay, thank you, Colin. Oh, add a note is from place, and then you have a note down here. Okay, yeah, so nets, I think it is, where is it? Oh, wait. Oh, man. Yeah, here, okay, so it's underneath the wire. You have your net label, and this is, it's good to put on every single, like if you have an IC, you put it on like the pin outputs, and this like Altium will automatically like, okay, wait, this one's V out. So if you name this V out right here, then the wires connected to this pin will be known as V out, and like Altium will be able to translate that, and they know that it's going through here. So if there's a junction, or if it skips over, it can keep track of that, and yeah, it just helps organize all your wires to those labels. And later on in layout, it'll be important because that's where it'll give you errors if you're not connecting them to the correct net label. So it's very important to have these on your wires. Here you have your 2 gains and ground. Puneet, do you have anything to add to that?
yeah, you've done a great job there. The one thing is, the reason you can also put like so many different ground ports is they're all connected to the same ground. They all have the same net. So when you go into PCB like schematics, they'll be like connected or have air wires to show that they're connected. You can also rename those ground ports to be different grounds if you have to use if you need isolation in your circuits between the grounds and between your power. So that always works.
Mhm.
Yeah, but in general, like if you have a net, you can also just get rid of the wire between 2 points if they're the same net, and they'll still be connected. So say you want it, so you see that that ground port that you have there, pin 4.
Yep.
Yeah, if you get rid of the line between it and
Okay.
just put a ground port, those are connected basically, right? Or if you just get rid of that ground port in general, that's already that pin's connected to ground, and it's connected to all the other grounds.
Yep.
So
It's very useful. Your resistors are. I don't believe so. Like manufacturers will just create the PCB or like the layout that you create afterwards, and then you'll be the one soldering on the components.
yeah, actually, but there are some manufacturers that you can tell to solder components on. They do charge quite a bit more, because basically what they're going to do is you're going to place the parts using a robot and solder them together using chip click or something and bake it in an oven.
Very fancy.
But yeah, so a lot of component manufacturers will do it. They will charge you a lot more for the components, and they will also charge you a lot more for the labor. And SMD component soldering is difficult depending on the size of the component. If you look at an SMD chart, if anyone wants to bring it up, there's different sizes. Usually, the easiest size to do is about 1206, and that's pretty much like a decent size. That's just a little bit smaller than like your normal through hole size. And actually, this will show you. So if you go to the surface mount, the picture next to this one.
This one.
Yeah. So what I'm talking about is that 1206 size, or where's 1206? Yeah, 1206 size is usually a good size to always work with. 0805 is not that actually bad. I've done all the way down to 0402, which is, the size of smaller than a grain of rice. Kind of just a little bit thicker than a strand of hair, but you can do it by hand. But yeah, no, if you stick to 1206 or 0805, there shouldn't be too much issues.
Yeah, I believe the smallest like recommended is 0402. But like,
I wouldn't even recommend 0402, to be honest. If you don't need to do it, I'd say the lowest you should go is 0805. But there are areas where there's a lot of components stuck together, mainly to improve either filtering for signals or because they're going to sit in this one, or because the board size is just so small. If you don't need to go that low, there's no point in going that low in size. 1206, 0805 is kind of the sweet spot for sizes. 0603 if you need to, but yeah, and try to keep your sizes consistent. You don't want to be ordering like 3 different types of the same resistor, because when you usually order components off DigiKey or wherever, the more you order of that single component, the cheaper it is.
Okay. Cool.
Oh, and for Y Imperial, PCB design is weird like this. So you'll notice everything will be either in inches or millimeters, just no standard. Manufacturers will just use whatever they want. And that's why Altium, you can switch between millimeters and inches when you actually do your part placement. I try to use mils, which is like thousandths of an inch, just because it's more widely used. But millimeters is also good when you're kind of focusing more on like board size. So if you have like and it's funny because most PCB manufacturers will use millimeters, but like when you go to data sheets and stuff, you'll see mils as the standard size, which is really, really dumb. So you can flip between them. It doesn't matter too much.
Yeah, and just to clarify, mil is like 1,000th of an inch, just what that measurement means. Okay, yeah, so is everyone caught up to the schematic? Just to have some feedback. we're nearing, I think, halfway. If okay, so if everyone's pretty much here, we can start creating the component schematic, which like these are for custom components that you want to create. Also, another point here is like this is okay to have it floating because you know it's going to ground. But if you don't have a net label, or you have a pin that you're not going to be using on an IC, it's important to place the generic note ERC, and that just tells Altium that it's like you didn't make a mistake. You actually mean to not use this pin. So it's just like a little X that you can place on a pin. So we can move on to creating a schematic. So this is for custom components, like I said. So in your project, this is going to be part of a library. So you can add new to project, and then you can add a schematic library. So if you click this, you'll see another sort of sheet-like thing, but it's not a sheet. Sorry, did someone want to speak? No, okay. For our schematic, we'll be creating the LM386. So here it's like for your custom component, you'll be wanting to look at the data sheet. So let's just go up. And the important part for this is looking at the pin configuration. And you'll see like the numbers and what the name is for each pin. So when you create the schematic, let's see. For Altium, first you want to create a box. So on this line thing, you can right click it and you can draw a rectangle. So this will just be the body of our IC. And you can press properties down here in the panels, and you can change the color if you want. I prefer it to be transparent. Another thing is designator and design item ID. We'll go over that in a moment after we place the pins. So for pins, you can just click this and you'll have a pin drag out. So you want to place the pins on either side of the IC with it connected to the body. So the side with the numbers, make this custom component. Yeah. So when you're in your on your sheet page, press project, add new to project, and then schematic library. And after this, we'll be making a footprint after our break. Let me know if you still have some trouble with that, and I can help you out. So these numbers should be inside the box because that's how the pin is connected to the IC body. So first we can look, so some generic like conventions is that inputs are on the left and outputs are on the right. So usually if you have power pins, they're on the top left and ground pins are on the bottom right. You want to group similar pins together. So if it's a very big IC, you want to group them together. And important thing to remember is that like the packaging for like the actual physical pins might not be laid out in this way. And that's okay because like as long as you make sure that the pin numbers are the same, it will correspond correctly onto the footprint and into your layout. So just make sure that for each pin you see on the data sheet, as long as you have the name and the number correct, it should correspond to this. So you can see this is like the package, right? And you have like the numbers in order, which is how it should be. But in your schematic library, you don't have to have these numbers in order as long as you have the numbers correct for each pin, corresponding to the correct pin. So we see that we have BS and we have ground and we have the inputs here. So those we can, for BS and the inputs, we can put on the left side. So let's just see. Okay. So you can double click. Oh, wait. And there we go. Name. So this, oh, wait. We can put the in first for the input. So we can do input in negative and in positive, which is 2 and 3. And negative. positive. And then we we have ground down here, so we can just place that. Let's see which pin it is. Ground pin 4. We have the out pin 5. We have our 2 gain pins, which we can put here. And we have 2 more pins on the bypass. And I believe 8, 1 and 8. Okay. 1, 8. S, which is 6. And bypass, which is 7. Okay, and then you also want to add a text here, which is sort of your designator sort of text. So this would be a U because it's an IC. Is everyone caught up at this point? Let's see. Oh, added the pins. It's top here. Okay, just put a comment in the chat just to let me know if you guys have caught up to this point. Yeah, so the numbering corresponds to the data sheet and it has to be the same as this. So as long as it corresponds to the same pin here, then it's fine. The placement for the pins, like where it is on the rectangle, doesn't have to be in this this like pattern this way, but as long as you have the number and the actual pin name are the same, that's the important part. So you can just double click on the pin and you can type in the name here. Or you can, I think you can just use the properties panel. Yep, you can just use the properties panel here. So if you don't have the properties panel, you can just click panels and add it here. All right, so an important part of creating the schematic, how did you get the U? This place text string right here. Click that and you can place text anywhere. And it, yeah. So another thing for the design item ID, you want to get the manufacturing part number from the data sheet or like the manufacturer. So I believe, where is this one? Oh, where is this? Oh, usually they do have like, am I not seeing it somewhere? Okay, I believe it's just this. Usually it has it like listed out. Oh my god. The manufacturing part number, which is what you want to name this just to, so that you know. And also the designator if it's an IC to make it U question mark. You can add a description if you want. Usually there's one provided by the manufacturer as well. Yep. Since there's no comments in the chat just yet, I'm going to give a little more time to get to this point. But after we save this, we can take a break and we'll be halfway through. After that, we'll be going over the footprint, which will be connected to this. And that's basically if you go to the schematic and you want to look down here for the component, show the models. So we've essentially created like the schematic here, and then after the break, we'll be wanting to put create this footprint. Where are we putting the element? So yeah, that's our main component. Do you mean in the schematic or? Oh, sorry, what are we changing the name of? Oh, Sam, could you clarify your question? I don't think I understand. Oh, the name, like on like this, the actual component manufacturer part number. Yeah. So design ID. So if you click like anywhere on blank space and then click properties, you can add it in the design item ID. Yeah, no problem. I think there was another question. What are we changing the name of? Changing the name of, like the pins, or not quite sure what you mean for you. Oh, okay, cool. So you can save this, and when you save it, oops, when you save it, you want to save as the same thing as this, just so that everything is organized and you're not just searching for random parts.
Oh, also, one key thing is you can also add supplier links to this part. So you go to the bottom right corner, edit supplier links. By that, you can kind of just add. And if you can find the component, wherever it is, it doesn't even have to be here. You could also find it on, yeah, there you go. National Semiconductor. Click that, press OK. And click that, OK. What I'll do is that'll add the supplier thing. And then there's also a way to add all the parameters from this to your component as well. So it would share all of the same parameters. So when you go in later and to see like, oh, what is this op amp rated for? Or, oh, what is this component rated for? It would share the same things. As well as the other thing this helps with is when you're making your BOM at the end, this basically already like puts like, you know, where to buy the component, the cost, and how much quantity you need. So it's useful to have.
Yeah, for sure.
Yeah, I think you can, if you go to add parameters, you could probably add them from there.
Sorry, how do I add parameters?
So if you go up, right there, add.
Oh, here, yeah.
Parameter, and then you can add proper parameters one by one. There is a way to add all of the parameters. It's a little bit weird. And actually, we can show that when we go back to the actual schematic.
Okay. I think we can do that now. And then we'll just take the break.
Sure.
Okay. Wait, no, for the actual
Go to
component.
components.
Yep. And then, is it here? Okay.
So if you add the component itself, are you trying to add the component, the schematic component we just created?
Oh, schematic component we just made. Oh, not really. For our layout, we'll be using like the manufacturer part one. This one's just to show how to make this.
Oh yeah, but if you just place it just for show, I can actually show how we can add parameters to it. So you go components to your library. When you add that, then if you go to manufacturer part search, you find whatever component you need for this.
Like this component itself?
Yeah, so just type in LM386. And this is really only happens when you can't, there's a component that doesn't actually have a supplier kind of given thing. So if you right click on this, you can do add supplier link and parameters to part. And then by doing that, just click on the part now. And they should be added, yes.
Okay, okay.
It's pretty weird, but yeah, so you can see like it's already shown up there on the bottom. There you go.
Yeah. Wait.
If you go to parameters on top there.
Sorry. Where? Here.
There, like the bar for parameters. That's the footprint bar.
This one?
Yeah, it should show. Yeah, there you go. All your parameters are added.
Okay.
for the components. So what it's rated for, all the pin ratings and everything.
Okay. Cool. Yeah, and this is the U is double because we've added the link to it in the schematic here. But if you didn't add it, you can just create your own there. Okay. Hopefully everyone's caught up to this point. We'll take a quick 5-minute break because we're a little bit behind schedule, but we'll take a quick 5-minute break right now, and then we'll come back and do footprint. So you can go grab a drink, some food. Yeah. Okay. If you have any questions, you can keep messaging in the chat, and we can answer your questions there. Okay. Let's just set a time. 4:15, so that's 7:15. We'll be back. How you added the piece to the schematic. Yeah, so if you go to the components tab in your panels, if you don't have it open, you can you'll open this bar here and it should show up because it's part of the project library. And when you click that, you'll have the design item ID will show up here and you can just drag that in. Okay, 5 minutes are up. Just let me know if you guys are back, and we will begin on the footprint. Thank you, Stephen.
You're welcome.
Let's have the video on. Okay. Just wait for someone to message. Just know that you guys are back. Awesome. Thank you, Chloe. Hey, okay, Floria. All right, so we will begin the footprint. So sort of the same, same from the schematic. So you can go to project, add new to project, and then instead of a schematic library, we'll add a PCB library this time. And you'll see this. So today we'll be using the Footprint Wizard because it's sort of just faster, and most of the time you want to be using that just because it's quick to go through and a lot easier to use. But there are a lot of tutorials online as well if you want to check them out on how to create like a footprint from scratch. So this is the part where we'll be needing to look at the data sheet and specifically the layout part measurements that Fahim was showing earlier. So these measurements. So if you go to Altium and you can do tools and you'll see this IPC compliant footprint wizard. You want to click on that and you'll have the footprint wizard show up. So just make sure everyone's got that. Click next. And we have SOIC, so you can sort of see that from here, right here. So you can choose the different packaging depending on what component you have. And these are like the packages, the type of package is listed here, and it even says like what it's used for, sometimes like inductor, diode, resistor. But today we'll be using this. Okay. And when you click next, you'll see all the measurements and a little chart here. So this is where the data sheet will come in handy. Oh no, okay, wait. I'm going to cancel this for a second just to speed things up. It'll be easier if I have it like this. Okay, cool. Let's do tools, IPC Footprint Wizard, next. SOC or IC. Okay, so width is H right here. You can see that is here. So make sure you look at the measurements correctly. This is like really easy to mess up. I believe, okay, so you see that this is in millimeters. So this should be in the brackets, should be millimeters, and inches in like non-bracketed. So here we have minimum is 5.8, which is already there, and then 6.19, which is already there. Maximum height A, okay, let's see. It's right here and is 1.75. I think this is set up from the last time I used it, so it might already be automatically placed in here. But yeah, so 1.75, you can see from this measurement right here. Minimum standoff height, which is A1, I think it's 0.1 right here. So we can change that to 0. Body width E, 3.81 to 3.98. And then we have body length range, which is D, it's right here. This should be 4.81 to 5. Got number of pins is 8. A maximum lead width range, which is B. The width there, 0.31 to 0.51. And then you got L here, which should be right here. 0.0. Okay. Cool, no questions. so if everyone's got that, so everyone got the thing, the measurements in. Also, we want to tick this generate step model preview. So that's just that's this 3D. So without it, it'll just be a box, and then they have like a fancy 3D model. So you generally want to generate that.
Right, Selena, quick comment.
Yep.
Certain people are not seeing the IPC compliant footprint wizard. Would the normal footprint wizard suffice, or?
I think it should be the same.
It is the same.
Yeah. Okay. Great.
So then, yeah, you can just use the footprint wizard.
Yep. Okay. So once you have that placed in, actually, if those people who are there, if you can like take a quick screenshot or have these measurements out, it's good. And then we'll move on to the next one. Pcb Library. It's project, add new, and then Pcb Library. Okay, so we can keep going. So some ICs will have a thermal pad and there's a ground pad. During that, like in the schematic, you would want to also add a pin for that pad. For this one, we don't have a pad, so we won't be adding one. Just some more values. We can just keep this as the default. Just as like an introduction, your default. Pad dimensions, I think this is fine. Yeah. 5.4. Yeah. If there are problems, you can change it. So I prefer rounded because or I think rounded is better because of like how it saves like the current or like the shape. So it doesn't waste like an extra copper corner. Screen line width. Okay, these are all good. These, depending on if you're working with a club, they usually have certain standards for which layers you want this footprint to be on. If you're working by yourself, it's up to you. So yeah. And then just use the suggested model, and you'll have creating a new one, and you'll produce the 3D step model. Otherwise, you can also download like a model and add it to it, but generally just having this generate is good enough. So you can finish that and you'll see your footprint show up right here. Okay. What pattern do you choose? Notepads, Shiki. And then pattern, I think you mean package, right? It should be SOIC. So we can maximize this. So now that you have this, you're basically you're set for the footprint, and you just want to save it real quick, and you want to keep the name the same as what the footprint name is. Save it here. Everyone have got to this point? Let's just see. Or knows how to get to this point, and then we can move on because we're running a little low on time. But for the schematic here, we can, we can add a footprint, and then I believe it will show up right here for us. Okay, wait, I'll go slower. So if you go back to you don't have SOIC in your list. Could a mentor help? And then I will keep going. So if you go back to your schematic, you can press add down here in the parameters, and you can add a footprint. If you click browse, after you've saved your PCB library, you should be able to see it right here. And you can press OK, and you've selected a footprint, and it'll load right here. So now you'll have a footprint there. And make sure you save the schematic after you've added the footprint. And then I think you should be able to see it now if you go here. Or models. and yeah, so you'll see both the footprint and this here, and it's still connected to the packaging, so it's a little odd, but it should be here. Okay. Anyone have questions? Let's see. Okay, if there are any questions, okay, we can move on to layout. So at this point, you'll be finished your schematic, and so you've so that was like if you have a custom component that you want to make, you'll have like the schematic there and the footprint, and then you'll create your schematic, which you've wired and you've created notes. You can do a quick design verification before you go on to layout. So if you go to it's design, no design. There's one that's you can report, create a report. There is validate PCB project. So you can validate it, and then if you go into your messages panel, you'll see some like errors and whatnot. All of these you can see are off grid. So off grid is like sort of negligible because it'll depend on your grid, and it doesn't really affect the functionality of your circuit. Let's see. So some of them have multiple names saying bypass and BS. Where did it just go? Okay. So multiple names means that the wires are sort of intersecting with each other. Maybe if I move that, it should be better. Okay, validate again. Okay. Yeah, so if they're connected to ground, then it'll have like an extra net name, or like it'll have conflicting net names. But other than that, it should be okay. So you can go through these like messages and just make sure there's nothing like really off about your circuit, just to double check before you move on to layout. So when you want to move on to layout, you can do, you can do panels, do projects. Okay, project, you can add new to project, and you can create a PCB. So this was where you'll be doing the layout. And when you click that, you'll have this board show up. And when you have this board, you want to first save it, or else you can't import. You can just do audio and layout. So now that you've saved it, if you go to design, you can import changes from your schematic. And when you import, you'll see all the things that you've added and changed compared to your current PCB file. And you can first validate changes if you're scared something's not right, and then you can execute changes. And when you do that, all your components, excuse me, will show up here. So these are all the footprints of your components. I'll just leave that back part. And you can just select all of them and drag them onto your board. So just for your PCB side, someone said, oh, Figim, is everything okay for questions?
Yes, somebody said that you did a step right after saving the PCB library, but I didn't catch what it was.
Oh, after saving the PCB library, you want to add it to your schematic. So if you go back to your like your schematic for the component, you want to go into here and press add footprint, and then you can browse and add the footprint that you just created. Okay.
Thanks.
No problem. So here in your PCB library, if you click your different keys, so this is currently on 2, this is your layout, and you click on 3, you can see your 3D models of all your components, and then 1 will be your board. So you notice that before we place anything, you just have your components here, and there are a lot of blue lines everywhere. These are ghost wires. They're called different things, but they're ghost wires. So basically they connect the different pins that, this is where your net labels comes in, and they connect the different pins that should be connected to each other. So you can have an idea of where your wires should go, where your traces should go. And the first step in layout is generally to open up the PCB. How did you get, oh, so to import everything, you click design and then import changes. So make sure you save the file first, or else you can't import the changes. But yeah, so you have your ghost wires here. And the first step in your layout is you want to move all your components into a position where none of the blue wires overlap. Because if they overlap, you know that your traces are not gonna, like, you can't connect the two without like going over each other, and you can't do that on one layer. So first you just wanna move around, like before we place any wires, move the components around so that they all fit and the ghost wires don't overlap. So, so the U1 will be the center of our PCB. C3 we know goes between the gains. So you see now that the footprint, the pins line up, it's 1 to 3, 4, all to 8. Even though we created the schematic in a different way, it corresponds to the different pins here. So C3, we have the 2 gains, so we can just place it above the IC. We have C4 that's coming from this pin. And you'll notice that there are a lot of pins, lines that are ground that are connecting to each other. We can ignore that for now, and I'll let you guys know why in a bit, but don't worry about the ground lines. Oh, sorry, that is totally not in the right position. Okay, let's see, J1, C5 we know is coming out of this pin here, like that. That's actually J2 over here. Microphone should be on this side. Okay, so this is really just a sort of placement, and I don't know, you can find it fun. I personally find it a little fun. Connecting wires. Okay, let's see. R1. Place it like this, and there are layout guidelines in the data sheet. You generally want to, you want to look at those, because for different PCBs, for different ICs, they'll have certain conditions that you need to meet. For example, like power converters, you need to have like a very short trace between it and it's like the inductor because of the switching. Also be aware, like it'll let you know about high current paths, and that will depend on how thick you want the trace. So it totally depends on your design. Just make sure that like the physical constraints are there, or requirements are there, and that you're aware of them. So let's see, I think that is pretty much, pins are on this side. Okay, so what is this? Oh, okay, so I just made a mistake. So if you, the screw terminals, if you look at 3D view, you can see that I just placed the inputs on the inside of the board, which obviously would not be very helpful. So you just want to rotate those two. Okay, and move C1 up. And then you'll see that like all the blue lines are not really overlapping anymore, except for the ground. And again, just don't worry about the ground just yet. So just have, has everyone imported and sort of placed somewhat? Shiki, did you import from the correct file? Oh, and make sure you save your schematic file, like here. So if there's a star, that means you haven't saved it yet. Save your file with all the components, and then it should update. So now that you have that, you want to save some board space. So this black is your entire board. So maybe just move it closer to the edge of a board, and then we can begin placing. So, okay, so we can first connect traces. So this is just regular wires. For example, so traces are here in this component right here. You click that, you can click a pin, and then it will create a trace. So we know those two are connected, and you can just create a trace like that. For each trace, you can change the thickness. Well, where's my properties panel? You can change the width and the length and all of that. So those are like for different, like high current paths, you'll need a thicker trace, for example. Okay, so again, you can see that if like after you place the trace and you sort of move a component, the trace doesn't come with it. So which is why it's important why you should have all your components placed where you want them to be before you start tracing, or else it doesn't work out very well. So let's just play that for a second. I actually want, okay. Add trace is top here, the toolbar. You have this interactively route connections. So this is a little spread out, but we'll let's say it's okay for now. So you want to add that. We can add this net, and now it's just a matter of connecting everything.
While Selena does that, I just want to make a quick remark that the traces typically, like as Selena is doing it right now, there's like no particular problem with just connecting them as they are, but sometimes you do need to consider the measurements as Selena has mentioned, depending on different amounts of current you're trying to deliver. And there's software available out there that helps you calculate how, like the dimensions of your traces and how large or wide they need to be for certain amounts of current to go through. I know one calculator is called Saturn, the Saturn calculator. You can use that to calculate the width of these traces. But for our purposes, since we're not driving a particularly large amount of current, having the traces of the widths that we have right now is acceptable.
Oh yeah. Also, when you're putting down stuff, there's a few good books on this, but there's like a specific way you should like put your components together, right? So when you're working with like high frequency or power components, there's like filter caps, things like that. You want them to be as close to your actual like switching regulator or whatever you have there as possible. And you want to make sure like you're designing so that it's not only designed in a smart way that everything flows well, but you're isolating the components that need to be isolated. You're providing the proper like kind of heat dissipation, things like that for some of the components that are there, because there are components that are going to heat up a lot. And a lot of times what PCB manufacturers do is put a lot of copper underneath it to provide heat dissipation. There's things like when you have signals, like high frequency signals, they can bleed into each other. So you want to keep them as far away as possible from the board, just to make sure that, you're not having any kind of data bleed, or you're not having any sort of issues that way. So there's a lot of like good ways to design PCB and layout, and this is like a key aspect of PCB design. Like you should, like layout is something that you should take into consideration a lot before routing anything. And kind of figuring out also how you're going to route things is also a really good thing to think about. It's not just mindlessly putting stuff down. Another thing to take into accommodation is polygon pores. Polygons are basically these giant like copper masses that you can define on your board. So you can use them as kind of ground planes, and that also helps with a lot of like dealing with high power signals. Ground planes also ground planes or power planes can also help with large currents or large voltages that you have to put on different components. So do look into kind of what is the requirements for your components, what's the requirements for kind of what you're driving the board with, current wise, voltage wise. Look at high frequency things. Look at if they're going to affect other things or be affected by other things, right? And design for that. And when you do, like, your board will be more, I guess, have a better chance of working out of the gate, or there'll be less issues.
Yeah, so talking about the ground plane, we can take a look at like how this board is actually created. So if you go into design and then layer stack manager, you can see it shows up. Oh man, okay. We have 2 layers, so boards can have like a lot of layers, and it goes like 2, 4, 8, 16. I don't know like how many layers you've worked with, Puneet, but so since our circuit is very simple, 2 layers is definitely enough for us. So like a ground layer, we can so here you can like add layers to the board and change what kind of material you want the dielectric in between them to be. So you have the top overlay, solder, and then 2 layers. So if we go to our amp, you can see all these tabs at the bottom, and let me just move this bar. So you can see all these tabs at the bottom, and these are the different layers on your board. So currently we've been placing all the components on the top layer, and now we're going to create a ground plane to connect all the connections. So on the bottom layer, we can, so after you click it, you're on the bottom layer now, and you can also see, if you go into panels, there is view configuration, and you can see all the different layers that you have, and you can like hide them if you don't want to see them. Example. So for the ground plane, actually our board is gigantic compared to our circuit right now, so we can actually change that. If you click 1, you'll be in the board, and you can click design, and you can edit board shape. So that will give you the power to shrink your board to a reasonable size. And then also if you have like a specific like 3D enclosure for your PCB, you can also change that to 2. You can also like change the shape of it by, if you go to design and you can redefine board shape, and this you can actually click like the shape you want. All right, so going back to the bottom layer, we can add a huge copper pour, which is right here. So you can place polygon plane, and if you right click, you can do some other stuff too. For now, we'll just do polygon pour, and we can just click the 4 corners of our board here. And you also want to click the corner that you started with to enclose it. So you'll see that it just placed like a huge red box. So this is like essentially creating like a rectangle of copper on that plane. And so now that anything that's connected to that plane will be like connected to each other. And important thing to do is if you go to properties here, you have to add a net label so that it knows which connections are being made to this board. So since we want this to be the ground plane, we can just add that there. And also it's a little bit in our way, even if we change the top layer. So we can go to view configuration and hide it for now, but we know that it's there. So now there's something called like a via, and a via is basically a connection to a different plane on the board. So for example, let's see. Oh wait, that's already connected. Okay, this capacitor goes to a ground plane. And you see the via is already a ground label, except if it isn't, you can go to properties and you can change the net here. So you can see that's sort of what a via looks like. It basically makes a connection like vertically instead of like horizontally on the plane. And if you create a trace between the ground pin of this capacitor and the ground pin of that via, it should connect directly to the ground plane. Yeah, okay. So like now this ground should be connected to the bottom layer, which has the ground plane. So you can create those vias for each of the ground pins that you have lying around, and that will create the direct connection to the ground plane instead of creating like more traces on your board, which can be inefficient. So these are like, it saves that extra travel distance for the current.
On top of that, for vias, you can change the size as well. your manufacturer, wherever PCB manufacturer you go with, will have a minimum recommended via size for everything. Another thing is if you take a via, you can actually just place it on top of the pad and it'll just share the same plane automatically with the pad, as well as it'll just be a connection regardless. So that's another cool way to do it. It's not like the best practice, but you can do it. So say you had the via on C1, the next to C1. If you just took that via and put it right on top of the pad, it would also work the same. Like that, exactly. Right. So another thing is for the polygon pores, don't take it all the way to the edge of the board, defined board. You want to give it a little bit of space because there's going to be tolerance issues when the actual board is going to be manufactured. So just give it a little bit of space. Usually you can keep a keep out layer or a keep out line around the edge of the board, which will also signify like the cut line. So that's a good thing to have there too. And that's just good practice. But you'll get more into it when you kind of define your skills for everyone.
Awesome. Okay, so you can see that the ghost wires have disappeared now because the connections are all made. Have there been any questions in the chat? If not, this is like you said, the manufacturing. So the via size, you can see I'm getting a warning for that it's like smaller than 50 mil. So that is something you should look out for. So for your that's the wrong one. Manufacturer. So for example, we'll be talking about sort of the JLC PCB. So if you go to a manufacturing homepage, you'll see like they'll have a capabilities tab, and down here they'll say like what they're able to make. So the different materials, how many layers they're able to manufacture. And then if you go to drill hole size, you can see for minimum via hole size is 0.2 millimeters. And I believe currently for me it's 0.3, so it should be fine. And minimum diameter and all these different specifications that you should be aware of if you're using that manufacturer. So that's just another check that you should make before you send your board off.
Oh yeah, and the more layers you add on your board, the more expensive it gets, and it gets a lot more expensive. It's not like a small like increase, like it gets exponential sometimes. There's also the option by some sub PCB manufacturers that do flexible PCBs. Those are really cool. Those are dual layer. They're maximum, I think, only 2 layers, but they're flexible, so you can actually like solder onto it and then kind of flex it in weird situations. Those are really, really expensive. I think a 10 by 10 will cost you somewhere like $100 to $200, which is insane. But yeah, do look out for those. Those are really cool to see. And for kind of reference, board PCB layers can go up, I think 13 or 14 layers from some manufacturers. And 13, 14 layers is about what you would have in like a laptop motherboard or a desktop motherboard.
Yeah, so like if you look at the stack, you can add like signal lines. So sometimes you'll have different traces, like it's impossible not to cross over. So you'll use another plane for that connection. All right, so for our board, we're almost done here. We can just add like, if you want to just sign off on it, you can always place, string, and oh, whoops, we are on the wrong point. So also you can see that you have like C4, C5, that is like the silk screen. So it gives you an idea of, so like when you're looking at it in 3D view, this is like how the PCB will look in real life. So you can see that. Something good to add is like, if you want just to show which side of these like screw terminals is positive or negative, just so that you know for reference when you're actually using the board, or to put any notes on like what this board does. So for that, you can go onto your top overlay, and then you can place the string. So we can say, like, for example, oh, I just placed way too many. Okay. Right, so plus, and then you can put a minus here. And etc. So if you want to add those like markers onto your board, it's always good practice. So you can also add sort of what this board is. So you can say like audio amplifier, what the gain is. I believe the one that we've created here is 200. Correct me if I'm wrong. You got the power, power, and then you got J2, which is this one here. Okay. So you can just move that and sort of add it here. And if you really want, you can like add your name here. Like if you're in a team, it could be designed by your name.
Also, if you can get a bitmap of your logo, you can also of a logo or something, you can also put a logo on it.
Yeah, that's good stuff. Okay, so that's basically complete. Oh wait, we want to talk about the BOM as well. So if you do report, you can click Bill of Materials, and that gives you a sheet of all of the components that you've used and all the materials you've used, and you'll be able to export a file here. So we can just export this, and if you click export, save it. Okay, we're here. And you can, that basically creates like an Excel sheet. Okay, this is, I think, a different one, but it's the same PCB. So we'll just create an Excel sheet like this with all your components, how much you've used, and you can sort of, like, you can alter how this is laid out within Altium as well if you need to.
Nice thing about bombs is the way you can configure them too is also have like supplier part links as well as like the supplier name. So DigiKey itself has its own like part names for each component. So it'll give you those, it'll give you a cost and all that stuff. So it's a pretty good, powerful tool to use when you're ordering your parts.
Wait, is it showing up here or? Oh no. Okay. Yeah. Okay. Fahim, would you like to talk about the Gerber files?
No, I
Sorry.
don't like your.
Fahim,
Hello?
Yep.
Cool. Sorry, I was muted. Do I have control of the mouse?
Oh yes, let me give you control.
Thank you.
Remote control. Okay, go ahead.
All right, cool. I'm just gonna move my webcam away because it was blocking the tabs. Alrighty, so right now we're on the JLC PCB webpage. We can go to the order now, and typically when you go to the order, when you order the PCB you'd like from a particular manufacturer, in our case JLC PCB, it'll ask you what files they'd like. In our case, they ask for a Gerber file. Or a Gerber file, if that's the appropriate pronunciation for it. To go and export our file to match the file type, all we need to do is go to File of our PCB document itself. If you do it for any other, you're not going to be able to find it. You go to Fabrication Outputs, and you'll see two options. Pick the Gerber file, not the X2 one. All these values can be configured. I believe they're already set to the specifications that JLC PCB is pulled with, so we can just hit OK. And you'll see on our right-hand side, we have the Gerber file. Wait. Okay, usually there's like a bunch of traces and such. I can see some, but all right, well, that is strange. Let me try that again. It might be a view problem. Okay, well, there should be the PCB should be like shown in terms of traces and such on this file. And then afterwards, if like you do have the Jupyter file ready and such, you can choose to send your the drill file, which is the file used to like basically tell their manufacturing like process, aka the robot that drills the holes, how to drill the holes. And so for that, you can just go to the fabrication options and then download the NC drill files. So these would be just the holes that would show up. And I just lost it. Strange. Okay, but seeing as how there weren't any problems in the compilation, that should be fine. Afterwards, you can just go to the JLC PCB, and then you zip them up, and then you put them into our, you put them in here as a zip file. And then over here, you can see all the specifications for all your, like for what your design needs. For example, the number of layers. As you can see, what Vineet said before is correct. The more layers you have, the more it will cost. You have the other specifications as well. I don't think I need to go through each and every one of them because they're all going to be tailored towards what your PCB design will do in particular. And then afterwards, you can just click Save to Cart and then order.
Oh, yeah, one thing is surface finish. So the HASL, lead-free HASL, those are basically like a silver kind of tin finish that they put on PCBs. So if you ever look at if they're like silver contacts, that's what HASL is usually. ENIG is gold. Usually if you're working with a lot more high sensitive components or kind of, you want to be a baller or whatever, the ENIG one is a little bit more expensive, but it is really good for kind of connections and things like that, especially on like some more sensitive components. That's why like most motherboard manufacturers and stuff do use gold pins on everything. All RAM boards have gold pins. It's just the connection's better there.
Thank you for that. Yeah, so as I said, these are tailored to the specifications of the board itself. So it really just depends on what you're designing. For our cases, we don't actually need to go the baller route, so to speak. So we can pick either of these. Lead-free one's obviously better for the environment, but I mean, it does cost a bit more, so take it as you will. And yeah. That about concludes the PCB ordering process at the very least. Sorry you guys weren't able to see it on Altium. When I tried it before on my previous files, I was able to see it just fine. It might just be a zoom in error.
Yeah, I think there you go.
I think it's because when we cut the board, we didn't center it afterwards.
Oh, you didn't set an origin point.
Yeah, so because of that, the origin point is like a lot further. It's like a lot bottom left to what.
Okay, yeah, that makes sense. Yeah, with the cam files, you can also, I guess, set up kind of like cut areas. So you can put borders and stuff around stuff. That should be good too. But this is good. Yeah, just when next time, like, for everyone out there, yeah, just make sure like you're setting your origin to the bottom left corner, bottom right corner, or whatever of your board. Don't put it in the middle because it won't work as well. But put it on the corners. But yeah, otherwise that's good.
Yeah. Yeah, that was my fault. Sorry.
No worries.
Oh no, I forget that all the time too.
Yeah. All right. I think that basically concludes our workshop. If you guys if any of the mentors have anything to say, thanks, Shiki. Yeah, we're basically wrapped up. If you guys have any more questions, you can feel free to message us. All the resources should be posted after this workshop's finished. The recording will also be posted and available for you to go back and figure out anything you weren't able to complete today. Yeah, you guys will have access to the recording afterwards. Yeah, so I think, do we have a slide for this last bit, just for fun? Okay, we don't, but thank you everyone for coming. I hope you guys learned something, learn how to use Altium a little bit better and make some fun PCBs for your own projects. All right, we'll stay on for like another 2 or 3 minutes if anyone has any questions, and then we'll close the meeting room then. Thank you for coming.
For those of you that are leaving, and Puneet is correct in saying that the lead one is easier to solder.